Now, which is a collaboration with Beshar Nas and Olaf Lancidol from Chalmers University in Sweden and Thomas Watain from Indriya in France. So let me start with the context of our work, which is low power mesh routing. Let me see if I can just get the live feedback from my monitor. Exactly see where I am in the slide. We can replicate it. Yes, that works. So the context of the work is low power mesh in. Good now? Yeah. No, it's cut. Okay. I'm so sorry about that. I'm going back to the previous one. Okay, so the context is low power mesh routing, so in IPv6 type of network. Yeah, where we have actually networks of autonomous and independent nodes that are going to form multi-purpose applications. One typical example is smart building applications where you're going to have smart plugs, smart bulbs, you're going to have appliances. All of them you actually purchase from different manufacturers. And the user is going to actually deploy them, and the nodes together are going to form a low power mesh network. That's actually a low power backbone, routing backbone, that's built to actually support any type of traffic that's not known a priori. And in this type of networks, distributed low power routing, the state of the art currently is achieving delivery ratios in the 99% delivery range. So this is state of the art. And the motivation for this work is that we believe we need better than that. We believe we need to get orders of magnitude better than that. Like 99% delivery ratios means losing packets in the percent scale. That means that losing is really part of your network operation, and your application has to actually account for losses. What we say is that we need to have a way more reliable mesh network where losses become really the exception. So you can actually start relying on your network and build robust and important applications. So what's interesting is that if you look at the state of the art in industry automation, well, you see that networks have been deployed for years now, and lots of them, and they've been achieving consistently delivery ratios like way above what we're used to, at least in this community. They've been achieving 99.99% delivery commonly, or even above that. And just to help you visualize that, this is 10,000 packets, the green dots that we're going to send. And at the top left corner, you have a red dot, which is one loss. So that's one loss per 10,000. And that's what we are aiming for today. Now, this is what we're starting from. This is 99% delivery. You lose one packet every 100. That's really, losing packets has become the routine, and we really want to go away from that and achieve truly reliable and robust mesh networks, even in challenging low-power IPv6 context. So the question we're asking here is, what can we learn from the work that's been done in this industry automation community? What can we learn from it so that we can actually build our own IoT networks, flexible networks that benefit from the same sort of reliability? So let me step back and present how these industry automation standards, wireless HART and ISA 100, actually do achieve such high reliability. And they do so by using a MAC protocol called TSCH, which stands for time-slotted channel hopping, which is part of the IEEE 802.15.4 standard now, which basically is TDMA in a time-slotted context. So nodes are going to wake up every 10 milliseconds and communicate. And the communication is going to happen on different channels, so that's frequency diversity. And all that is dictated by a schedule, which is obtained running a scheduler that is usually distributed or centralized, most traditionally centralized. So here we have one example schedule. It's basically a two-dimensional array. On the x-axis you have time and y you have frequency. And the schedule is actually, here we have a simple example of 4 nodes with a schedule produced centrally that actually tells, so at every point in time, so here what you need to understand here is that every cell is a 10 millisecond slot, and that the duration of that schedule or slot frame is 11 slots here. That's just an arbitrary choice for this presentation. Here we have 11 slot frame. And that means that the schedule is going to repeat every 11 slot and going to cycle for the whole lifetime of the network. And here we have one example schedule that tells to the nodes what to do at every point in time. So at every point in time, you know if you should be sleeping and saving energy, or if you should be listening on a particular channel, or if you should be transmitting on a particular channel towards a particular node. And so the scheduler has very high responsibility, you know, in the network operation, but it can actually produce very time and frequency efficient schedules that can achieve contention-free communication, meet very tight latency requirements, and so on. Now the problem is that this requires a scheduler, and this is difficult to apply in IoT scenarios where we need all the flexibility of the IoT. So we have multi-purpose application in the IoT, where in industry context, you have single purpose and the whole network and schedule is tailored to single application, which can be like data collection or actuation, but the application is known a priori, it's known by the scheduler, and that's not the case in the IoT. The second difference is that in industry automation, we have an integrated network, so everything is built at once, the nodes are known in advance, they are usually homogeneous, it's not changing so much during the lifetime. In IoT, we need something much more flexible with node addition at runtime. The nodes are heterogeneous. They need to operate independently and autonomously. So the way we tackle that challenge of bringing TSCH to the IoT is through something that a new approach that we call autonomous scheduling, which I'm going to compare here to the traditional approaches in TSCH, namely centralized and decentralized scheduling. So I'm going to briefly show how this traditionally works in TSCH or in any scheduled network. So here you have a very simple network example. And what's going to go on in the centralized case is that a central entity which is located at the network, root, or gateway, so any central entity, is going to collect data periodically on the link quality, on the application needs, and then it's going to compute a schedule that optimizes for some metric, and then going to disseminate the schedule back to the node so the node can actually start running by that schedule. The second approach, which is a bit more flexible, is the decentralized approach, where you have the same network here, and every node is going to locally compute its own needs in terms of scheduling, and then it's going to exchange, so either end-to-end, doing like end-to-end path reservation to actually install slots all over a given path, or they're going to negotiate with the neighbors specific slots. Now, what we introduced to make scheduling possible in IoT flexible networks is what we call autonomous scheduling, where you have no more than local computation and there is no extra communication involved. And the way we can do that is pretty simple, is because in IoT scenarios, we have a routing protocol that is running anyway, which is distributed routing protocol. It can be RPL, it can be something else. In our paper, we are considering RPL, but the approach is generic. So here we have this routing protocol that is running, and that's actually giving, you know, information on the neighborhood and the network to every node. And what Orchestra does, our system, is going to exploit that information to build schedules deterministically so that nodes can communicate with any of the neighbors at any time and support any type of application and traffic planes. So let me introduce Orchestra, which is a solution for autonomous scheduling in TSCH networks. And it has actually a number of properties. So the main idea in Orchestra is that we're going to exploit the routing state, and in particular like the neighbor and the routing tables. And we're going, for instance, to exploit properties of our neighbors, such as the MAC address. We're going to use, for instance, the hash of the MAC address to infer, you know, a slot that we must be listening or transmitting to, and so on. Then Orchestra has different types of slots, which I'm going to present shortly. Each of them providing different trade-offs in performance and also providing different services, like able to support different services. We have per traffic plane over provisioning of our schedule. So what this means is that the over-provisioning part is because we want to support any type of traffic that's unknown a priori, very much unlike what's done in wireless art. So we do over-provisioning and at the price to pay in Orchestra. But the nice thing is that we can do that per traffic plane. So every traffic plane has independent schedules that are produced, and each of the schedule and traffic plane is going to, cycle independently and not interfere with each other. The last interesting aspect of Orchestra is the energy guarantees. So because it's completely scheduled, we can actually infer lower and upper bounds on energy consumption, which can be very important in certain scenarios. So the reason Orchestra is achieving very high reliability is we have three main reasons. The main one is it guarantees consistency between routing and scheduling at all times by design, simply because the schedule is inferred locally from the current routing state and at instant. The schedule is updated instantly whenever the routing changes. Second, we have actually control contentions. So we can reduce contention, or we can even in certain cases, we can eliminate contention altogether, and that's going to have a tremendous impact on reliability. Now, the last property that gets us high reliability is channel hopping, which once we actually manage to get TSCH to run in these scenarios, actually comes for free, thanks to TSCH. So now introducing the first type of slot that we have in Orchestra. So it's the simplest one, the most basic one. It's actually a rendezvous slot that's used for neighbor discovery and routing. It's fully contention-based. So here we have a simple example network of 4 nodes. The y-axis is going to be time, and this is one schedule, or one slot frame in the TSCH vocabulary. So the slot frame is made of 7 slots of 10 milliseconds each. So that's one particular schedule. It's going to repeat, to cycle, for the whole lifetime of the network. So this is what the schedule of node 1 looks like. And all the other nodes are going to have the same slot frames and slots. So in TSCH, nodes are globally synchronized and running the same slot frame structure at all times. Now in the rendezvous slot, we have a single slot that is common to all the nodes. So all the nodes are running the exact same slot at the same coordinate in the schedule. Here, the first slot. We're not showing the channel offset here for simplicity. It's a yellow slot because it's used, which means transmit or listen. So in practice, you wake up for that slot. If you have something in your queue, you transmit. If you don't have something in your queue, you keep listening. And this slot is going to repeat at every slot frame, so every 7 slots here for the whole lifetime. And what this brings you actually is the ability to communicate with any of your neighbors. So that's really for discovery. For instance, like if 1 transmits here, 2 happens to receive the packet, and we start actually building a topology. And that's done simply by the upper layer. It's totally transparent to Orchestra. So the routing protocol is going to say, oh, I received something from 1. I'm going to use that as the next hop. Now 2 is transmitting, 3 and 4 receive. Same thing happens. We have a full connected mesh now. So note that this is fully contention-based. It's not an efficient type of slot, but it's a very convenient one because it enables neighbor discovery even in this scheduled context. Now the second type of slot, which is more tailored toward efficiency, it's for unicast transmission. This is a receiver-based unicast slot, shared slot. So the idea here is that we still have the same slot frame length of 7, and every node is going to have 1 receive in green here. Green is receive, blue is going to be transmit. You have 1 receive slot at every node, a single one. And this receive slot is basically at a time offset, which is a hash of the MAC address. For simplicity here, it's the node ID. So node 1 wakes up at the first slot to listen, node 2 wakes up at the second slot to listen, and so on. And now all the other nodes that actually want to communicate with 1, 2, 3, or 4, they're actually are going to maintain a transmit slot, a blue one, at the time offset of the receiving slot, which is, again, a hash of its MAC address, or here, node ID. So 2 wakes up at slot 1 to transmit to 1, 3 wakes up at slot 2 to transmit to 2, and so on. So we have a few example communication going on here. 3 transmitting to 2. It's a unicast. It actually received an ACK in the same slot. This is as per the TSCH standard. Now we have another example here. 3 and 4 both attempt to communicate to 2, and this is to illustrate that this is still, shared slot. meaning contention-based slots. So we still may have contention here. The 2 nodes content, they don't get an ACK. They're going to back off, use an exponential back off as per the TSCH standard, and attempt to retransmit some randomized later time. The last type of slot is the sender-based shared or dedicated slot, which is pretty similar to the previous one. Instead of having 1 receive slot at every node, we have 1 transmit slot at every node. Here, based on the node ID. So node 1 wakes up at 1 to transmit, node 2 wakes up at slot 2 to transmit, and so on. And here, same principle, nodes actually are going to listen to whatever neighbor they actually want to receive from. So in this simple example, where we only assume single directional communication, all the traffic is going to 1, for the sake of simplicity here. 1 wakes up at slot 2 to receive from 2, and 2 receives at slot 3 and 4 to actually listen to 3 and 4. I know that's one communication between 3 and 4 going on, and the nice property here that we can have in the same slot frame communication two packets sent to node 2, which we couldn't in the previous case. So the basic trade-off difference that we get between sender-based and receiver-based is so sender-based has much less contention and can even be contention-free. However, it's also more expensive because it requires to maintain 1 receive slot for each neighbor, which will mean actually wake up and listen more often. Now I wanted to illustrate an important property of Orchestra, which is the autonomous maintenance, autonomous slot schedule maintenance. So still in the same example, we stick to the same sender-based schedule. Node 3 is going to switch next hop from 2 to 1. So the way it happens that it's going to add 1 as a new next hop, and then it's going to instantly update its schedule. So it's going to actually, so meaning that node 1 is going to start listening to it. Next, it removes its old link, its outdated link, and node 2 is going to remove the slot because it doesn't need to listen anymore to 3. Finally, final part of our design, I'm showing how we put all that together. So we have the different type of slot that I've introduced. Now, the way Orchestra builds a schedule is by having different slot frames, each of them assigned to a particular traffic plane. Well, that's really key in Orchestra. So we have, typically we have the MAC control traffic, we have routing traffic, and we have application traffic. And each of the slot frames going to cycle independently. We use co-prime lengths so that's to ensure the cycle is independent, and the slot frames interact in a fair way. So I'm going to show an example here. So we have a first slot at the MAC layer for TSCH beacon of length 7, I believe. Yes, length 7 here, and it is for receiving TSCH beacons. It has a single green slot installed, and that's going to this single receive slot is going to cycle every 7 slots. We have a second slot frame for another traffic plane, independent of the first one. That one has a different length, length 5. It has a single slot, which is a rendezvous slot, the yellow one. It's used for routing neighbor discovery. The last one, and the third and last one, is for application. Here it's a sender-based. It could be anything. So it has a length 9. It has 1 transmit and 1 receive slot. In practice, it's going to have multiple transmit and receive slots. This is, again, for the sake of simplicity. And now at runtime, what's actually going on is that we don't have slot frames anymore, so we don't have like the vertical, thick lines. What happens at runtime is that every slot, we just select, vertically. If there is any active slot, we use it. If there is no active slot, we sleep. In case of what we call scheduling collisions, where you have 2 slots overlapping in the same in your schedule, we select the slot belonging to the slot frame with the highest priority. So we can prioritize slots and slot frames. So here in that example, routing has higher priorities than application. The consequence of that is the nodes are going to skip 1 communication slot, so it's going to add some latency. However, no communication is going to happen at all in this slot. This is to show a practical example of how this is running for real in the testbed. So we have 98 node testbed here. It's Indriya. The x-axis is time. We have a 40-minute experiment. The y-axis is nodes. We have 98 nodes. what you see here, you have diagonal orange lines that show you it's receiver-based slot, and they cycle at some frequency. Then we have blue one that cycle at another frequency, and we have the vertical green ones that is for rendezvous. It's vertical because every node is waking up at the same time. So we don't need to see the details here, but it's really looking at the shapes. So let me jump into the evaluation. So we implement TSCH and Orchestra in Contiki. We run over 200 experiments in 2 different testbeds, experiments lasting up to 72 hours. The 2 testbeds are respectively 98 nodes, Indriya, and testbed that we've built at 6 of 25 NXP nodes. And what I would like to stress here that our solution is fully platform independent. It works both, on legacy platforms such as the TLOSB or state-of-the-art platform to the NXP, the JN that we're using, which is 32-bit MCU with very high-speed crystal oscillator. So I'm starting with the most important result here, which is reliability. That was actually our end goal. So this is in Indriya. We're comparing 5 different cases. Always on is a basic CSMA, so it's a non-power saving Mac. Nodes are always on and transmitting. Then Contiki Mac is a state-of-the-art low-power listening of Contiki. Then you have TSCH min, which is a minimal solution, minimal schedule for TSCH, which basically is the simplest schedule you could come up for TSCH. It's a single rendezvous slot, repeating at some period. So you have a single slot for everything, all the traffic planes, unicast, broadcast, and so on. Then we have the Orchestra receiver-based case where we have 3 different traffic planes. We have MAC routing, and for application we use receiver-based. And the last one is the same, we're using sender-based for application. So now the results here on the x-axis, you see different protocols. On the y, you have the packet delivery ratio. First observation, CSMA achieves quite good results, 99.9%. But bear in mind, this is not power saving, it's always on. So that's not practical in low power mesh. Next, Contiki Mac is in the 99 range. TSCH min with a very basic schedule does not really help. Now Orchestra with a sender-based or receiver-based schedule gives us 99.996% delivery. So that's about 1 loss in 30,000K, in 30K. The next evaluation was to show that we support any type of traffic, including with RPL, with downwards routing. So there was yesterday mention of how difficult it is to route downwards with RPL, and that's definitely true. And I have talked to the authors, and we understand together like what's going on in our respective experiments. What happens at TSCH plus some enhancement of the routing protocol that we do enable having strong downwards routing even with RPL. And what you see here is that you have mostly symmetric links, and that's partly thanks to these 2 mechanisms. The end-to-end delivery ratio achieved with this downwards routing case was 99.98%. Now on the energy bounds, I'm comparing here Contiki Mac to TSCH and Orchestra approaches. So what I wanted to stress here is with Contiki Mac, you don't really get any usable energy bounds. So the upper case, the worst case with Contiki Mac is like you're transmitting all the time and you get 88%, that's not really usable. Now with Orchestra TSCH sender-based, you also don't get very usable bounds. So meaning that with Orchestra, you don't always get usable bounds, but in certain scenarios, so whenever it is needed, you can come up with a schedule such as this receiver-based one that will give you very interesting bounds, such as maximum 3%. No node will spend more than 3% on. And that's a very important property for many applications. Last experiment is a simulation. I'm actually closing the loop and comparing now our TSCH plus Orchestra approach to the more traditional centralized scheduling. So what I've shown previously was that it was possible to have TSCH in the flexible IoT domain. Now I'm comparing against the more traditional centralized. It's mostly to characterize how much we lose in comparison to centralized, because Orchestra is doing over-provisioning, so it is losing in terms of performance. And the top part is not the one I'm going to focus much on. It was mostly to show that Orchestra is able to recover from routing adjustments. But the main important thing is to notice the duty cycle. We have to pay a 4-to-8 ratio price and latency factor 10. So we have an important price in terms of over-provisioning. Let me conclude now. So I have presented this autonomous scheduling approach that actually enables bringing TSCH to low-power IPv6 IoT scenarios. And so we show it's possible to run TSCH in such context, and that's actually partly possible with over-provisioning, and I just showed like the price to pay with that in comparison to centralized. Now the result that we're very happy with is that we improve reliability by 2 orders of magnitude, so we go from 99 to 99.99% delivery, and that's for a number of reasons which I've detailed before. I'm not going to repeat this for the sake of time here. I would definitely invite you to try it out. We spent a lot of effort on the engineering of that. It's 2 years of effort. It's very strong protocol that I really invite you to use. It is tested for interoperability in Prague in July, so it interops with the other reference implementations. It's BSD soon in the main conti key, but currently available on that GitHub. Thank you for your attention.